Hello, I'm Nguyen. I'm from Wimmics team of India, Sophia Antipolis, and laboratory I3S of University Côte d'Azur. Today, I will bring to you the research relevant to use on multi-objective evolutionary approach for mining class Disjointness Axiom. I'm a representative of the group of two authors. Another one is Andrea Tetamazi. At the time, we witnessed the growth of linked open data, which become the big data repository to extract knowledge. And the formalization of the knowledge we approach here is called ontology. In this, the axiom play an important role to validity of the knowledge in ontology. Our research is relevant to extract of this important axiom from the IDF repository. Among various types of axiom, we focus on a mining class Disjointness axiom. Like all the types, the class Disjointness axiom are important to check the correctness of a knowledge base and to derive the new knowledge. In this approach, in this work, we follow the extensional approach to suggest axiom based on the instance in the dataset. Specifically, we use evolutionary approach, which called the grammatical evolution for this learning task. Grammatical evolution is a grammar-based form of genetic programming, and in grammatical evolution, the search space consists of variable length string, which is distinguished from the solution space, and the bit string are mapped into the programs tend to BNF Grammar, and based on the functions. The rules in the BNF Grammar are chosen in the mapping process. A grammatical evolution approach for extracting axiom are given in some previous course. And a general methodology of this approach is indicated in the workflow. And in the generation of the axiom, an initial population of class Disjointnism are created. These axioms are the phenotype with mapping from the genotype in the form of integer string. And based on the BNF grammar, and BNF grammar and BNF grammar play an important role for formalizing the where-from axiom, and also for expressing the fact content in the ADEP repository. And thanks to the mapping process, the integer string will be mapped into the phenotype in the form of the old axiom. And then the improvement of initial population of axiom are performed by evolutionary operations through the crossover and mutation operators. And in the evaluation phase, the axiom will be tested again to the ADEP repository through the various quality and measure and the fitness function. And realities in the previous works, we focus on the extract class Disjointness axiom using the traditional grammatical evolution. On those, we get the good result to extract this kind of axiom. However, the previous work contains some limitation. The first limitation relevant to the diversity in the often population, and the second one relevant to the case when the often axioms are possibly invalid even though their fitness values are too high. So it requires some necessary improvement to reach a more effective model to mining axiom. the new model should improve the diversities of the resulting population of the axiom, and also allowing to trade between operative in the fitness function. In this work, we focus on extending the grammatical evolution approach in the previous work in exploring class disjointness axiom as a multi-operative problem. And we can call this approach a multi-operative grammatical evolution. And then we focus on optimizing the evaluation framework for the axiom to ensure the high accuracy, generality, and the diversities of the obtained axiom. Specifically, we treat the problem as a multi-operative optimization problem, which allows for explicit trade-off relevant to a set of objectives, in which all objectives are equally important. It means that finding the optimum solution cannot be based on one objective alone while skipping the other objectives. The term domination is used for the situation of comparing two solutions. A solution dominates the other solution if it's no worse than others in an objective. The sets of optimal solutions are denoted as a Pareto optimal solution, which correspond optimal objective vector, which are denoted Pareto optimal front or non-domination front. And in the graph, we can see the point C is not for the Pareto front because it's dominated by the point A and point B, while the point A and point B are not strictly dominated by any other point. So they do lie on the front, which we know as the Pareto front. A heuristic approach of multi-operative optimization is a multi-operative evolutionary approach. We can call shortly MOEA. And MOEA it refers to finding multiple non-dominated points as close to the Pareto optimum front as possible, and it's called Pareto optimum front approximation. And MOEA also provides operators such as crossover and mutation operators to improve the involving non-dominated points. A well-known algorithm of MOEA is called NSGA2. It refers to find non-dominated solution with the elliptic and diversity preserved mechanism. And in this work, we follow this algorithm to apply the multi-operative optimization. As the particular case of MOEA, the approach we propose comprised the integration of GE in MOEA using NSGA, specifically using NSGA2 to develop a multi-operative model of axiom discovery, which we call the multi-operative grammatical evolution. We can call shortly MOGE. And basically, the mechanism of MOGE is quite similar to the one of MOEA, exception that we define multi-operative problems using the integer arrays, integer string, which we know codons. Codons will be considered as decision variables, and the codons do not define axioms themselves, but they provide instruction for deriving axiom based on the BNF grammar in the mapping process. And we comply with the BNF grammar given in the previous was to mind the binary disjointness axiom relevant to complex expression, which contains relational operators, and in the grammar indicates the three relational operators are intersection, existential quantification, and value restriction. And an example of a small sample of an adept dataset indicated in the slide. And based on this example, adept a sample of an adept dataset, and based on the previous BNF grammar indicated in the previous slide, we can give an example relevant to the mapping process. From the chromosome, we use the function in the mapping process. We can induce to the axiom in the form of our language. Relevant to multi-objective evolution framework, the goodness of an axiom is determined by its dominance index. Is often a score on each object, which is not dominated by the corresponding score of another axiom. And relevant to the qualities measure, we reckon axiom scoring, which are relevant to possibility and generality, which we apply in the previous work. And possibilities is a reliable measure of the credibility of the class disjointness axiom. And possibility is measured by defining the number of counterexamples and the support. And the value are counted by executing the corresponding background query. And the generality of an axiom is measured by the minimum of the cardinality of the extension of the two class expression involved. And finally, in order to ensure the diversity of the often axiom, we use a score of the similarity of each axiom to the other axiom in the population in the new evaluation framework. Then we develop the separate two objective functions to evaluate the quality of each axiom. The aim of objective functions is to obtain axiom which maximize the value, possibility, and generality, while not being too similar among themselves. The similarity measure of an axiom are computed by the average of a similarity matrix between it and each remaining axiom in the obtained population. This computation requires the computation of similarity between two axioms, and which is defined based on the degree of similarities of their expressions. And each expressions will be transformed into the binary tree, and the definition of each similarity between expressions is performed on based on the corresponding binary tree. And the trees are transferred at the same time, and each pair of corresponding nodes in both trees is compared to each other. And the returned value is the degree of similarity between the two nodes. And in the table, we can reference the similarity degree between the two nodes. And here is an example of computing the similarity degree between two axioms, phi1 and phi2. We can see in order to compute the degree of similarity of them, we need to compute the quality between their expression. And here, so we have the four as a pair of expression we need to compute. There are AC, AD, BC, and BD. And in this image is an example how to compute the similarity between the expression A and C. There are similar ways to compute for the odd pairs of expression, And finally, the similarity of axiom is the maximum value of them. To investigate the effectiveness of our approach, we organize our datasets following the model of the training testing. Specifically, the learning process is performed with the input data source, which are derived from the training's IDF dataset. And the random sample of Wikipedia, while the evaluation of a discovered axiom is based on the testing dataset, which is the entire Wikipedia. We modify and integrate grammatical evolution in NHGA2 algorithm, which were developed in the MOEA library on the Java framework for multi-objective optimization. And we run the experiments on the different parameter testing, which indicate in the table. And in order to allow fair comparisons, we define the total effort, which reflect the total number of the fitness evaluation, and is computed based on the population size and multiplied with the number of generations. We reuse the definition of precision based on fuzzy set cardinality in the previous course to measure accuracies of the model. And over the 20 runs of the experiments on the MOGE, we obtain the number of the valid distinct axioms for most parameter testing is significantly greater than those matched by the single objective grammatical evolution methods in the previous course. Also, the result confirm that the proposed methods have the high accuracies. Specifically, the precision value are equivalent to the figure of a GE method, with the higher than 0.98 for the on different population size and different number of generations. And we also consider the possibility and generality distribution of the axiom, and we can see the number of the highly qualified of axiom is still maintained in the MOGE system. Besides, based on the specific resulting statistics, the number of the obtained axiom from MOGEs in the best testing is much greater than those the figure extracted by the grammatical evolution, and with the smaller value of a total effort reflecting the cost of evaluation. It means the MOGE is clearly more effective inducing highly qualified axiom. We also consider the distribution of discover axiom in the best testing in relevant to the similarity coefficient, and we can see the run of similarity. Consider record for this axiom belong to below 0.35. It means there is a good diversity of the classes and the properties in the components of axioms. And in the slide indicates several examples of discovered axiom with the high qualities of axiom with a high possibility and high generality. To approach to the full set of valid distinct axiom, you can follow to the link indicated in the slide to approach it. In this work, we apply a multi-objective extension to grammar-based genetic programming to axiom discover with the two objectives in addition to similarity score. We also and we can see the experiment result confirm that this proposed method is capable to discover the high accuracy and general axiom, and is more effective compared with the single objective methods in the previous course. And in the future, we focus to my disjointness axiom relevant to the further types of complex class. And we refer to develop the more axiom scoring to estimate the qualities of axioms such as complexity. Thank you for your attention.